All right, welcome back again, everybody. Today we're going to be doing section 13.3, which is all about, well, a lot of stuff. So let's go ahead and get started. Yeah, 13.3. So this section is titled Arc Length and Curvature, but the amount of content in this section is substantial. So this is definitely one of those lectures where you may want to take a break in the middle because it's going to be a little bit long. It's just packed with so much stuff. So let's get started. First, we're going to talk about arc length, then the arc length function, then we're going to talk about curvature and the various curvature formulas. This is actually one of the reasons this section is so long. There, you're going to notice a theme where it's like we get a definition of a thing like curvature, and then we're going to get one formula for it, and then another formula for it, and then another formula for it. And for each one of these, there's just like three of these formulas. And we're going to derive most of the formulas so that you can see where they come from. We'll talk about the unit, normal, and binormal vectors. Then we'll talk about osculating and normal planes, osculating circles, torsion, and then we'll finish up with some helpful Mathematica commands. And I actually have I have a nice Mathematica animation in here that we can use. One thing to mention about all of these different formulas, like even the torsion formulas, you don't need to have those formulas memorized. I will give you those formulas. What's better is to make sense of what they are and where the formulas come from, and just to be able to visualize what these vectors and what these amounts really are giving you. All right, so let's get started. So first, okay, before we talk about arc length, remember to define the arc length, you need a continuously differentiable function. So a function is continuously differentiable if it's differentiable and its derivative is a continuous function. That's what it means to be continuously differentiable. Basically, the derivative is also continuous. Um, Note that just because, so when f is differentiable, we're automatically given that f is continuous as well because differentiability implies continuity, right? But not the other way around. But here we're saying something a little bit different. We're not saying that f is continuous. We're saying f prime is continuous. So I have this little counterexample. Think about the function square root of x defined on the interval 0 to positive infinity. Well, if you take the derivative of f, what you will find is that you lose a point of continuity. So f prime is not continuous on 0 to infinity. It's continuous on 0 to infinity, excluding the point 0. So we need our derivatives to also be continuous. So here is the arc length. You might remember this for arc length of a curve in R2. So you should remember this from Calculus 2. If you don't, I have a lecture on it on my YouTube channel. I think it's section 10.2 from the Math 8 playlist. Is it 10.2? I think it's 10.2. But if you remember from back in those days, we were able to define the arc length of a curve as the parameter t passed between alpha and beta. And it was defined this way. And one of the things that I love about this particular formula is that it's very intuitive because it really is just the Pythagorean theorem. It's the Pythagorean theorem. This is a squared, this is b squared, and then when we take the square root, we get the length of c, right? So the whole idea, if you remember from Calc 2, the way that you came up with this formula was you basically used approximating line segments, and then you took the limit as those line segments shrunk to nothingness. And then that gave you this integral. Well, in higher dimensions, the process is identical. So how do you find the length of a space curve? Well, you start by using finite line segments, right? You use a bunch of finite line segments, you add up the lengths of those line segments, and then you push the number of segments to infinity as their length goes to 0. And so then you get a more general arc length formula. For us, we're going to stick to 3 dimensions for now, just to do this right here. So this is the definition of the arc length of a space curve in R3. So if you've got a curve that's defined by this vector equation, then the length of the curve is given by this formula here, which again is just a natural generalization of the formula that was on the previous slide, or this slide right here, right? Here it's dx dt, dy dt. Now we're doing dx dt, dy dt, and dz dt. And more generally, this formula holds for any number of dimensions. So this formula holds in general. The length is really just adding up the length of the tangent vector at every point from A to B. That's it. That's what it is. So that's the arc length. Um, yeah, so what's nice is to think about this intuitively as well. This is a nice representation because remember, this is a r prime is basically your velocity, right? It's like it's the tangent vector. So it's telling you where the curve is going and how fast. Well, taking the absolute value just gives you the speed all on its own. So really what you have here is speed times time, and you're adding up speed times time at each moment. Well, speed times time is distance, so it's how far you've gone, right? That's what this is really saying. Take the speed, multiply by the time, you get the distance, add up all those distances from A to B at every moment, and you get the total distance, the total length. Like I mentioned before, this generalizes naturally to any curve in Rn, even R2. And the generalization to any dimension just follows from repeated applications of the Pythagorean theorem to find the lengths of the approximating line segments, just as we saw in Calc 1 or Calc 2. So this is the arc length formula right here. All right, let's start playing around with it. Here's one I want you to try on your own using that formula. I want you to find the length of one arc of the circular helix given by this. We saw this in the previous section, right? Uh, one of the previous sections. And I want you to find the length of the arc from this point to this point. So first off, just think about it for a minute. And then say something out loud about how you're going to start. Remember, you don't have to say, you just got to say something out loud. You don't have to say it to anybody necessarily. And now try to compute it yourself, and we'll do it we'll do it together in just a moment. All right, here we go. So first thing we got to do is compute the derivative. So we compute r prime, we get that. Then we need to find the length of that vector, the length of the tangent vector. So we're just going to use the distance formula basically. We get this, which ends up being root 2. So now we know that r prime of t is root 2. And then we use our formula. So what is the length? Well, see, if we're going from this point to this point, and our integral is in terms of t, we need to know what values the parameter is passing between. But luckily, once again, we can see here that this z component is just given by t. So that means this is when t equals 0, this is when t equals 2 pi. So we're getting one arc from 0 to 2 pi. In this case, the length is constant. So the length is root 2. So very simple application of FTC2 gives us that the length is root 2 times 2 pi, or 2 times square root 2 times pi. All right. So one thing to keep in mind is this. A curve can be represented by more than one vector function. So this is an important thing to remember. We talked a little bit about it when we were talking about lines earlier, but what this means is this. The parameterization of a curve is not unique. So in other words, how you describe the curve is not a unique description. You can describe it in lots of different ways using different parameters. Here's an example right here. This is a curve t squared, t cubed. It's actually equivalent to this curve down here, e to the u, e to the 2u, e to the 3u. The difference here is t is going between 1 and 2 here, and t is going between, I'm sorry, u is going between 0 and log 2 there. And the way that this occurred is we just made the substitution t equals e to the u. So the important thing to realize here is that the curve itself has not changed. So doing this substitution does not change the object which we are describing. It's still the same. The curve is still the same. What has changed is the way we represented it. The parameterization has changed. It's kind of like, yeah, it's like changing the labels. And you might have some other details that go along with it, but the curve has not changed. All right. So in other words, what this means is arc length is actually independent of parameterization. And as a result, the arc length function is well defined. So this is one of the reasons that oftentimes we will reparameterize curves in terms of arc length, because then you don't have to worry about like what coordinate system you're in or what parameter you're using. You can just use the arc length itself. There we go. So Suppose that a curve C is given by a vector function. We're just going to do R3 for now, or V3 maybe I'll say, xt, yt, zt, where r prime is continuous and c is traversed once as t increases from a to b. Then the arc length function, or as I like to call it, the length so far function, is given by this formula here. Now I want you to just kind of stare at this for a minute. Look at that formula for a minute, make sense of all the pieces, and then I'll talk about it again in a second. All right. So again, for those of you that took me before in is it Calc 2, maybe Calc 2. Calc 1 is where I start this. This is one of the reasons that I really, really hammer everyone about these area so far functions and just blank so far functions, because that's what this is. This is a function that is giving you the amount of something so far. It's an accumulation function. That's what it's doing. It's adding up a bunch of stuff. And the input of this function is the upper bound. So you're basically saying where to stop the sum. So what we're saying here is that you can define a length so far function just as we saw here. So the formula is still the same. The only thing that is changing here is this upper bound to give us the length so far. Now, what we can do is we can apply FTC1, which is like the best one in my opinion. Apply FTC1, and what you get is you get this. ds dt is the function that's inside, evaluated at the upper bound, right? And this lets you, or this translates to ds is equal to the length of r prime times dt. There you go. ds is equal to length of r prime dt. So yeah, so this is actually, I kind of said just a minute ago, this is handy because arc length arises naturally whenever you're talking about kind of like any curve. And this does not depend on a coordinate system. I mean, arc length does not depend on a coordinate system. So oftentimes we prefer to parameterize our curves with respect to arc length. So that way we can basically say where you are in the curve based on, I'll say, the length that you've traveled so far. That's the idea. So we're going to do this one together, and I'll kind of explain as I'm going along. So let's reparameterize the helix. Oop, typo right there. Let's reparameterize the helix that we've seen, that we know and love, with respect to the arc length, measured from the point 1, 0, 0 in the direction of increasing t, so kind of the natural direction. Here we go. Like we saw before, this point corresponds to when t is equal to 0. And from earlier, we calculated that the length here, the length of that tangent vector is square root of 2. So by the result we just saw a moment ago, that means ds dt is square root of 2. And so that means that ds is equal to square root of 2t. I'm sorry, square root of 2 dt. All right. Now, what is our arc length so far function? Well, this is what it looks like right here. This is the arc length so far from from u equals 0 to wherever you want to stop, wherever you want to stop. Just lost my train of thought. That du gives you this dt. Yes, exactly. Okay. So s is equal to square root of 2 times t. And so that means t is equal to s over root 2. And now we're going to reparameterize in terms of s. I'll go back through this in just a moment here. Basically what we got was we got a relationship between the arc length and t. In fact, maybe I should actually highlight this piece just to emphasize it a little more. So s of t over here, that's the arc length so far, and we got a function for it. This is the arc length so far. Now what we're going to do is we're going to solve this for t, and we get this value right here. Now what we're going to do is we're going to take this value and we're going to plug it in everywhere we see a t in our original parameterization. So our original parameterization was this. This guy right here, this is all in terms of t's. When t is equal to this, this is that. When t is equal to this, it's equal to that. What we want to do is replace all of those t's with s's somehow. But in order to do that, you need to compute this relationship right here. You need to find a functional relationship between the arc length and the and t, the parameter. So that's what I'm doing here. Now I'm going to replace t with s over root 2, s over root 2, s over root 2. And now this vector is all in terms of s, which is nice. So what this lets you do is it lets you define the vector based on how far you have traveled along the curve. So this vector function is saying, hey, if you know how far you've traveled along that curve, I can tell you exactly where you are. So it's a little bit different. There's no Cartesian coordinate system going on or polar coordinate system going on. It's really just like how far along the curve are you? Okay, then I know exactly where you are. All right, so now let's talk about curvature. So we need a definition before we can talk about curvature, and it's this notion of a smooth parameterization. So we say that a parameterization r of t is smooth on some interval if the derivative of r is continuous and it is not equal to 0 on that interval. So we also say that a curve is smooth if it has at least one smooth parameterization. I like the intuition as always. Intuitively, all we're really saying is that a curve is smooth if it doesn't have any sharp corners or cusps. So when the tangent vector is turning, it's turning continuously. So we don't want curves that are like super jagged, like the Weierstrass curve or something like that. A little side note at the bottom here, this is not the standard definition of the term smooth that's used in later math courses. So some of you might hear this word smooth later on. The more common definition of a smooth function is one that is infinitely many times differentiable and the derivatives are continuous. So just beware that some of you, when you hear this word smooth later on, it usually is a much stronger condition. It basically means you're infinitely many times differentiable. That's basically it. And every one of those derivatives is continuous. All right, so we need something nice. We need a smooth curve, and then we can start to talk about curvature. So let's let C be a smooth curve defined by the vector function r of t. Remember from the previous lecture that the unit tangent vector is just taking the tangent vector and dividing it by its length. Here's a very nice picture of that, actually. Should have included it in the other lecture. There we go. So what this vector function gives us is the direction of the curve at any time t. Now, take a look at this picture over here, this figure. The direction of the tangent vector will change slowly when C is more straight, right? It'll change slowly the straighter C is, but it'll change very quickly, for example here, when the curve is sharply twisted. So like here you can see the curve is actually pretty gently smooth right here, right? Arrows, arrows. But then right about here, the tangent vector changes direction rapidly. That's the notion of curvature. That's what we're trying to get at. How do you explain that this curve is extra curvy? Extra curvy. Well, this is how you define it. So we say that the curvature of a curve C at a point is a measure of how quickly the curve changes direction. It's a measure of how quickly the tangent vector is changing direction. So more specifically, it's defined like so. This is the Greek letter kappa. So kappa of S is the length of dt ds, where t is the unit tangent vector. And it's always nice to kind of phrase things in these ways, in like a just straight language, right? In other words, we're saying the curvature is the size of the rate of change of the unit tangent vector with respect to arc length. Whew. Okay, that's a mouthful. Let's go back and look at that figure one more time, just to make sense of this a bit more. So in this picture, zoom in a little bit, each one of these little red arrows is the unit tangent vector. That's the unit tangent vector. It's pointing in the direction of the curve, the way the curve is going. And what we want to know is how fast it's turning, right? So if we're talking about speed, like how fast something is turning, we're talking about a derivative. So in this case, we're talking about the change in the unit tangent vector. Change in the unit tangent vector. Okay. Now, we want to be able to quantify the change in the unit tangent vector, but we're going to do it with respect to arc length so that we're not married to a specific parameterization, right? We don't want curvature to depend on the coordinate system. That's not really what we're looking for. We're looking for curvature as something that only depends on the change in the tangent, no matter what coordinate system you're working in. And that's why we define it in terms of ds. So really what we're looking at is the change in the tangent vector with respect to arc length. And then we're just going to take the size of that. We just want the size of it. And that will be that's curvature. So that's how we define curvature. All right. Oh, a lot of this stuff I kind of already said, so I might move through it a little quickly. Intuitively, if the change in the tangent vector is very large, but the change in arc length is very small around some point, then the curve is very curvy there. Very, very curvy there. So if you've got a really rapid change in direction over a small interval, that's going to be a very curvy curve. Reciprocally, if the change in the tangent vector is very small over some long arc length, then that means the curve is not very curvy there. It's a lot more straight if the tangent is not changing much over a long period of time, or a long sorry, not time, over a long distance, I'll say. If the curvature is actually zero, so imagine this is zero for a minute. This. So if that is zero, then that means that dt has to be zero. So if dt is zero, that means the tangent vector is not changing at all. And so if the tangent vector is not changing at all, you've got a line. So lines have zero curvature. That's the idea. Lines have zero curvature, which makes intuitive sense, right? Because a line is not curving anywhere, it's going straight. If it starts doing this, your curvature can't be zero. If it starts doing this, your curvature can't be zero. If you're always going in a straight line, the curvature is zero. There's no curving going on. Um, oh yeah, and this is what I already said. So yeah, generally we want this to be with respect to arc length, because arc length is independent of parameterization, so it'll be true in any coordinate system. Now, however, this is where the formulas start coming in. However, oftentimes it's a lot more convenient to compute the curvature when you can express it in terms of a parameter that is describing the curve itself, right? So it's nice that we have this general idea of curvature, but what about computation? Straight up, how do I compute it when I have a vector function given by r of t equals blah, 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 blah? Now we're going to derive a formula for it. So here we go. Um, Remember the good old chain rule from back in Calc 1. The chain rule gives us this result. So the change in the unit tangent vector with respect to t can be rewritten as this product here by the chain rule. So d capital T dt is equal to d capital T ds times ds dt. Now, if we move things around a little bit, massage things a little bit, we can solve for dt ds, which will give us this. Take the absolute value and we get this. And then now we can say that the top here is t prime of little t, and the bottom is s prime of little t. All right. And then since ds dt is the length of r prime, we get the following formula. But before I move on, this is something that I want you to just kind of stare at. Look at this calculation and make sure you can follow where each piece is really coming from. All right, so just kind of look at this for a minute. All right. All right, let me go back to this. Oh yeah. So remember, ds dt is the length of r prime of t. So we get the following formula right here. Boom. So the curvature kappa of a curve r with respect to its parameter t is given by this formula here. So I do want to take a moment to make sense of this because I'm going to flash back and forth a couple times here. Look at the top here. So this is t prime of t. This is the change in the unit vector. This is the change in the unit tangent vector with respect to t. This is the change in arc length with respect to t. But earlier we found that the change in arc length with respect to t is given by this, just by the arc length formula. So now we have a formula for kappa with respect to t instead of s. What is that formula? It's the length of the unit tangent vector divided by the length of the tangent vector. I'm sorry, I said that wrong. This is the length of the derivative of the unit tangent vector divided by the length of the tangent vector. All right, so again, stare at this for a minute, look at it, try to make sense. There's a lot of like tangents and derivatives floating around here, so pause and just look at this for a minute. Okay, now let's talk about this note. I have a tendency to mix these types of things up because there's so many like t's and little t's and big t's and primes, and a t is a prime and a prime is a t, all these things, right? So this helps me keep things in line in my head. In general, t prime is not a unit vector. So this is one thing to keep in mind. Remember that t of t is the unit tangent vector, right? So t of t is a unit tangent vector. T, like capital T, is unit length. However, we are now differentiating that vector. So we're taking that vector and we're differentiating it. So what we're really doing is we're looking at the change in this vector. And the change in that vector certainly depends on the curve, right? So you can have a unit tangent vector, but the way that that unit tangent vector changes depends a lot on the curve. So beware, this is not, it's not just a unit vector the whole time. Okay. Um, okay. Yes, so now we're going to show that the curvature of a circle of radius a is 1 over a. And I'm going to do this one, and you can all follow along, and then I'll kind of explain what I'm doing as I go along. Right. So first we're going to center the circle at the origin, and we're going to give it a standard parameterization, a cosine t, a sine t. Now we're going to basically use that formula that we just computed, or just derived, to compute the curvature. Take the derivative, and we get this. And then if we take the length of this vector, just using the distance formula, we get that it is a, which also makes sense. Makes sense if you think about it. Okay. So now we have this information. So the unit tangent vector is what we get when we take r prime and divide it by its length. So that's exactly what we're going to do. We're going to take this and divide it by its length. And when we do that, these a's are going to cancel. And so now we have that t of t is this vector right here. All right, so that's t of t. This is the unit tangent vector. Maybe I'll emphasize that here. So this is unit tangent vector. And now we're going to do the derivative of that vector. So we're going to compute the derivative of t, and we get this. So this is t prime of t, right? So now we're almost there. We're getting more and more pieces, right? What we really need is we need the length of t prime, and we need the length of r prime. So now we need to finish up by computing the length of t prime. So again, just using the distance formula, we get that the length of t prime in this case does happen to be 1. Just a coincidence, just a coincidence. That is not always the case. Now we can use our formula kappa of t. This length is 1, this length is a, and we get that the curvature of a circle of radius a is 1 over a. There it is. Okay, this is another one where I'm going to throw up the thinker for a minute. Just look at this calculation, make sense of what you're seeing, and make sense of all the pieces, and then we'll move on in a moment. Yep. All right. So move that out of the way. Yeah. So what is this really telling us? So this is saying that the curvature of a circle is inversely proportional to the radius. And this kind of makes intuitive sense too. So what we're saying is as the radius gets smaller, the curvature of the circle increases. So as your radius goes to 0, the curvature goes to infinity. And it makes sense if you think about, again, if I have a very large circle and I want to look at the unit tangent vector, right? Tangent vector isn't changing that much, but if I shrink that circle down to something very tiny, well, now the unit tangent vector is changing a lot, right? It's actually changing quite a bit as you go around the circle. So that's exactly what's happening. So as the radius gets smaller, the curvature increases because those tangents are going like whoosh very quickly. As the radius gets bigger, you can see that the tangent will not turn nearly as much when I have a big radius. So the curvature of a circle is inversely proportional to its radius. All right, now here is another formula for computing curvature. So again, this is just like formula piled on formula, piled on formula, piled on formula. There's so many. Um, the last formula we got was helpful if you wanted to compute the derivative of the unit tangent vector and do all that kind of stuff. Now we have another formula that just lets you compute a couple derivatives, throw it into a cross product, and then find the length and take some absolute values to get it. So this one is a little bit more systematic, and basically you have to compute r prime and r double prime, assuming that your function is twice differentiable. We're not going to do this proof. The proof is actually quite lengthy, but I don't think it's exactly edifying at this point, although I do encourage you all to read it on page 945. What do? You basically use the formula that we just proved a moment ago, and you use properties of the cross product. That's really it. But like math majors, take a look on page 945, read that proof. For the rest of us, we're just going to take this formula as it is right now and then use it in a moment here. Okay, now it's time for you to try this. So this one I want you to try on your own. See if you can find the curvature function of the twisted cubic and then find the curvature at the origin. And what I want you to do is use this formula. Use this formula here, okay? So, well, maybe I should have said think about it first. So think about what you're going to use and then say out loud what you're going to use. And now try to go through the calculation, compute all those things, find that cross product, find some lengths, and then we'll do it together. Okay, here we go. All right, so first thing right off the bat, we need r prime, r double prime, and these lengths. So here we go. Here's r prime, easy derivative. Here's r double prime, easy derivative. Now we're taking the length of r prime. This one doesn't really simplify. Again, these types of calculations can get very messy. That's okay. Just take a deep breath. Don't let it overwhelm you. You've still got the equality. Like you know what you're working with. You know what you are using. Sometimes things get a bit messy. That's okay. That's why we like we like concise notations sometimes. Now, this calculation can be a little bit lengthy because you're computing a cross product, which is a lot of arithmetic. Just use the determinant notation that we talked about back in 12.4. Compute the cross product of these two vectors, and you get this right here. Remember now, this is actually a good time to use that Mathematica command. So try to compute the cross product by hand, because that's what you'll have to do on a test, for example, and then throw that into Mathematica and double check your answer to be sure that you did it correctly. Super quick, super helpful, and then you can proceed, move on from there. Now I think we have almost all the pieces. Yeah, almost all the pieces. Next, we need the length of this cross product. So again, using just the distance formula, essentially compute this cross product, the length of this cross product, and you get this. Then throw everything together, and we get the curvature formula, or curvature function. So let me just emphasize this. This thing here, this messy looking formula over here, this will give you the curvature of the twisted cubic for any value of t. Any value of t you want. You want to know what the curvature is at 0, you can find it. You want to know what the curvature is at 10, you can find it. and so on and so on. So we were asked to find the curvature at 0. So we're just going to take t equals 0 and plug it in for all of these, and we get 2. So the curvature is 2. Definitely not a line, decently curvy at the origin, and that's about it. All right. Okay. um, Oh, wait, where am I going with this? Hold on. Oh yeah, so another formula. So in the case that we have a planar curve represented by a function y equals f of x, so this is like back when you're in Calc 1 kind of thing. What we can do is we can choose x to be our parameter, and we can write the vector equation of this curve like so. This is another good thing to kind of ponder. So let me just throw the thinker up for a minute. I want you to just ponder this expression here, I'm sorry, this equation here, and recognize it as a representation of a planar curve that is a function of x. Right? There we go. So what we're saying now is if we want to define the curvature of such a thing, a curvature of like a curve that you've been seeing for a long time, we can use that curvature formula that we just used in the previous example. That's what we're going to do right now. So what is the derivative of this with respect to x? It's this. What is the second derivative? Well, derivative of a constant is going to be 0. So we lose this and we just get this. So r double prime is that. Again, this kind of makes sense because if you think back to Calc 1 when you were first learning about the second derivative had a lot to do with curvature, right? Had a lot to do with concavity and things like that. So that is popping out here again. It's manifesting and reminding us that, oh yeah, second derivative kind of has to do with concavity and curvature. Now we're going to compute this cross product, and this is the result. This is one that I encourage you to do on your own just to verify that you do actually just get f double prime x k, right? And we also know from, geez, what is it, Calc 1 or Calc 2, that the arc length formula for a planar curve given as a function of x is this little guy right here, everyone's favorite from way back in the day. So using the formula from corollary 2, we get a new formula. So the curvature of a twice differentiable planar curve y equals f of x is given by this formula right here. That's it. Just like another version of it. Okay, here's another one for you to try, all right? So I want you to try this one on your own. Find the curvature of the good old parabola y equals x squared, everyone's favorite, and find the curvature in general, and then find the curvature at the points 0, 0, 1, 1, and 2, 4, all right? So think first about how you're going to try it. Right? And now just say something out loud just to, wake your brain up. It's a lot of information to process so quickly. So say something out loud to yourself. Maybe like, right? And now try to work it out on your own. Also groaning. All right, here we go. Well, we have this formula here that we can use. We just need to compute two derivatives, and that's kind of it. Compute two derivatives and then plug in some points. So here we go. Y prime is 2x, y double prime is 2. Plugging those into our formula, we get this. So this is the curvature formula for that parabola. And now we just evaluate the curvature function at those three values of x, 0, 1, and 2. So the curvature at the origin is 2. The curvature at x equals 1 is this value, 2/5 to the 3/2. So we're talking about the curvature right here at this point, 1, 1. Yep. And then the curvature at x equals 2 is about 2/17 to the 3/2. I mean, it's equal to 2/17 to the 3/2, which is about this value. And that point is, further along up here somewhere. Just like that. That's it. Now, One thing to kind of note, remember curvature is kind of telling you how curvy the curve is, right? So it makes sense that right here at the origin, things are going to be very curvy. There's a lot of change in the tangent vector there, the direction of the tangent vector. So right at the origin, the curvature is relatively large. But then as we move away from the origin along the curve kind of starts to straighten out, right? Remember, this goes to positive infinity. And as we move along this way, the tangent vector isn't really turning very much. Sorry, isn't really turning very much. It's just kind of going like up, like so. So that's why you see the curvature decreasing as x goes to infinity. It's like things are straightening out, whereas right here, things are pretty curvy. So one of the things that I like about this particular figure is that it's showing you a comparison between the function itself, which is y equals x squared, and the curvature, kappa of x, which is this blue curve right here. So like I was just saying, right at the origin here, the curvature is maximized. That's where the parabola is the curviest. But then as x goes this way, the curvature converges to 0. Things are straightening out, right? Relatively speaking. And then same if you go this way. So y equals x squared and kappa of x. All right, so let me go to this slide, and I'll say this. This is a good time to maybe take a break. It's already been it's been about 40 minutes, so now's a good time to stretch, go to the bathroom, grab some tea, grab some sparkly water, crack your neck, crack your knuckles, take some deep breaths, look at something that's not your screen. There's always the rule, right? Every 20 minutes, you should look at something that's 20 feet away. So let's just look for a minute. Mm-hmm. All right. Okay, so hopefully you all took a break there, and now let's come back and let's get through the rest of these. So now we got to talk about two other very, very important vectors, and then I've got a pretty nice animation for you to check out here too. So at any point on a smooth space curve, there are infinitely many vectors that are orthogonal to the unit tangent vector. So think about this for a second. If you've got a unit tangent vector traveling along a space curve, well, there's infinitely many vectors that are orthogonal to that curve. So maybe if I imagine my finger here is the tangent vector, right? Well, if we wanted to find a vector that was orthogonal to it, here's one of them, my thumb. But there's many others, because if I twist my hand, my finger is still the unit tangent vector, but my thumb is moving around. So there's infinitely many of these vectors that are perpendicular to my finger, the tangent vector, right? But there are two very, very special orthogonal vectors that are ones that are important, and those are the normal vector and the binormal vector. So we basically have the unit tangent vector, and we have the normal vector, and we have the binormal vector. All right. Okay, now we're going to talk about those. So remember this example from the last lecture, I believe. If the length of this vector is always constant, then we know that r has to be orthogonal to its derivative. Now, since the length of the unit tangent vector is always 1 for all t, we know that t prime has to be orthogonal to t. Okay, ponder that for just a second. Length of the unit tangent vector is constant. It's 1. So that means it has to be orthogonal to its derivative. Yes, that's right. That makes sense. Okay, now, intuitively, t, the unit tangent vector, is always pointing the direction the curve is going, the way the curve is heading. And t prime is always pointing in the direction the curve is turning. So the curve is turning in the direction of t prime. And that's where we get what we call the unit normal vector. So let r of t be a vector, let t of t be its corresponding unit tangent vector. Then for any point where the curvature is not 0, we can define the unit normal vector, sometimes called the principal unit normal vector, as this vector right here. There we go. the unit normal vector. And again, t prime is basically telling you which direction the curve is turning, right? It's turning that way. So tangent vector is pointing somewhere. Because t prime has to be orthogonal to it, if your curve turns, t prime is pointing in the direction of the turning, the curving, you could say. So t prime is pointing in the direction that the curve turns, and we're going to make it a unit vector, so we divide it by its length, and we get what's called the normal vector. Unit normal vector, my apologies, unit normal vector. Okay, so this is another one. Just look at this formula for a minute, try to make sense of it, try to remember this one, and then we'll get the binormal vector in a second. All right, here we go. So what is the binormal vector? The binormal vector is what you get when you cross the unit tangent vector and the unit normal vector. That's what it is. So that's called the binormal vector. So by construction, it's a unit vector that is orthogonal to both a curve's tangent vector and normal vector at any given point. So, okay. Let's try to put this all together. This is the unit tangent vector. This is telling you where the curve is going. This is the unit normal vector. This is telling you which way the curve is turning. This is the binormal vector. This is basically a vector that's orthogonal to both of these ones. And so all together we have this. And I have a nice animation that I'm going to show you in just a moment here. So all together we have the unit tangent vector, the unit normal vector, and the unit binormal vector. There you go. So this is a nice slide to take note of. It's got all the formulas. Now, this forms what we call the TNB box. So you might have heard of this before. So together, these orthogonal vectors Tn and B form what's called a TNB box, or a TNB frame, or a Frenet-Serre frame. And this is basically a box that changes as your parameter t changes. So what you could imagine is depicted in this figure right here. And then I've got a nice Mathematica animation. Here is the curve. This is the space curve in blue. And then what we're saying is that at each point on this curve, there are three vectors of critical importance. The unit tangent vector, which says where the curve is turning. I'm sorry, the unit tangent vector, which says where the curve is going. The unit normal vector, which says where the curve is turning. And then this unit binormal vector, which kind of says where the curve is twisting. And now we're going to explore these types of things for the remainder of the lecture here. Okay, now, hopefully you can kind of imagine this. So what I want you to do is just look at this figure again and just, let it marinate in your brain for a minute, and then we're going to look at an animation. All right, here we go. Okay, so what I want to do is just show you what this TMB box looks like as it moves around a particular curve. So let me switch over to Mathematica here. There we go. Yes, we're going to come back and use these other commands in just a minute, but really this is the code that I wanted to look at. This is code that I found online. You can just Google it, Google visual, Mathematica visualize TNB box, and you'll see a couple people's examples of how they did this. So we're not going to go through the entire code block right here. If you look at it, you can probably pick out pieces of it. But what we're going to look at is we're going to look at the TNB box for the trefoil curve or trefoil knot. We actually saw this back in, section 12.5. I can't remember. We did see this curve in a previous section. I just don't remember which. One command I do want to point out is this command manipulate. So manipulate actually produces a widget that lets you manipulate things. So it lets you manipulate the parameter here, and that's what I'm going to do. So, and what's being plotted here is the curve itself. So the curve is this trefoil knot. Okay, that's the trefoil knot. And then we're going to show the TNB vectors. So the blue vector is the unit tangent vector. This blue vector right here, you see how it's like pointing in the direction the curve is heading? The red vector is the normal vector. So if you look at the red vector there, it's pointing in the direction the curve is turning. And then the purple vector is the binormal vector. So the binormal vector is pointing in the direction, you kind of think of it as where the curve is twisting. We'll make more sense of that in a few slides here, but this is what it looks like, all right? So here's a curve. Here's the T and B frame right here. And now what I'm going to do is I'm just going to play this animation so you can see how it moves along with the point. There it is. Let me pause. Let's look at it from a different angle here. One thing I want you to notice is notice that the blue vector is always pointing, the tangent vector is always pointing in the direction the curve is going, right? And that red vector is always pointing in the direction that the curve is turning. And that purple vector is kind of accounting for twists that are moving like up away from that osculating plane. That's kind of what's happening here. We're gonna talk about those in a minute. Let me just pause and move the parameter manually. There we go. Just move it forward and back here a little bit. There you go. You can kind of see it right there. The perspective gets a little bit weird, but that's what it looks like. So these vectors are basically forming what's called an orthonormal basis, but this is what's forming the T and B box. So these things, like the T and B box is critical because if you ever need to talk about things like, I don't know, how things move in 3D or 3D optics or anything like that, you're going to have to talk about this T and B frame and where these vectors are pointing. Again, we want that they're all unit vectors. We want them to be unital because we don't want to worry about scales and lengths. We just want to know about directions, right? This will be included on Canvas. You're welcome to play around with this, dig through the code if you're interested. You can do these types of things, all that kind of stuff. You can play it, you can pause it. So, have fun. But this is the thing that we're talking about, and this is the thing that we need to be able to calculate, and this is the thing that we're going to calculate right now. So let me go back to the slides. All right, here we go. This one I want you to try. I want you to try this one. And remember, this slide right here, you can always go back to slide 34, and that will give you just a quick box of those three T and B vectors. So here is the question. Find the unit normal and binormal vectors for the circular helix cosine t sine t that were in example 1. Remember, we already found the unit tangent vector, so you can use that result from earlier. But maybe I should have thrown this up first. So first think about how you would start it. Okay, now say something out loud about what you're going to do first. And now get computing. So try to calculate it yourself. What is T? What is N? What is B? And we'll do it together in a moment. All right, here we go. Did we compute this earlier? No, I can't remember. So let's compute T first. So R prime of T is equal to that. Just do the derivatives of these component functions here. The length, yeah, we did do this earlier. The length of this is root 2. So now we have the unit tangent vector. It's just this, dividing each of those, each of these component functions by square root of 2. So we got one of them, the unit tangent vector. Now, how do we find the unit normal vector? Well, we need to differentiate the unit tangent vector. So same kind of thing. We're going to compute the derivative of this. And when we compute the derivative, we get this. Then we need to find the length of this vector. I don't show this calculation here, but you're welcome to verify it on your own for practice. Just use the formula for the length of a vector, the distance formula, Pythagorean theorem, whatever you want to call it, and you'll find that this is the length of T prime. So now we have the the derivative of the tangent, the unit tangent vector, we have its length, so we can compute the normal vector, which is this. Right. One little note that I have at the bottom here. Already this calculation shows that the normal vector to the curve has to be horizontal and points at the z-axis, which makes sense if you think about the fact that we're using this, we're looking at this circular helix. Remember the circular helix, imagine the picture of it. Well, as the tangent vector spins this way, the normal vector, even the unit normal vector, the non-unit normal vector is always going to be pointing inward, kind of like inward toward the center. So maybe if I drew this picture right here, right? Here is the tangent vector. The normal vector is always doing this. It's pointing inward, right? That's why this component is 0. It's not pointing up. It's not curving up. That's where the binormal vector comes in. So now we got to compute the binormal vector. How do we compute the binormal vector? We take t, we take n, and we compute their cross product. Here we go. Cross t with n. I pulled the constant out to the front just to save a little bit of calculation. And then you get this. All right, and then there we go. Thus, those are all of them. Unit tangent vector, unit normal vector, unit binormal vector, and this gives us that right there. So that is those are the T and B vectors, and you can form the T and B frame for the circular helix. Okay. Now we got to talk about osculating and normal planes. So some of you might have been thinking about some of the planes that are associated with this as we were talking about normal vectors. Because the last time we talked about normal vectors, we were talking about a vector that was orthogonal to a plane, right? Well, we're going to kind of expound upon that now. So with these important vectors, we get 2 important planes of interest, plus a third one that you'll see in the activity. But the first plane of interest is what's called the osculating plane. Osculating plane. This is the plane determined by t and n. So here is t, here is n, and this blue plane that you see in the figure, that is what we call the osculating plane. All right, so it's the plane determined by t and n. Yeah, that's right, yeah. And yeah, there you go. So this is basically the plane that comes the closest to containing part of the curve C near the point P. So this is the plane that is most likely to contain the curve if it were a planar curve. So that's why I have this note down here. If you have a planar curve, the osculating plane is just the plane itself. So this is one of those minutes where, again, I want to throw the thinker up and I just want you to stare at this, look at this picture, and visualize this plane that you see here, the osculating plane. All right. Now, the other plane of interest that we're going to talk about is the normal plane. So the normal plane is the plane that's determined by the vectors n and b. And that's this green plane that you see right here. This plane is called the normal plane because it is it's the plane that's orthogonal to the unit tangent vector. So this one I always think of as like, if this pencil is the unit tangent vector, this is the normal plane. So as the thing moves through space, right, the normal plane is my hand right here. The osculating plane is the one that's like, oh geez, maybe I can do it this way. Ah, maybe like this. The osculating plane is kind of like this sideways one, if you want to try to imagine it like that. And then this other note. So when you have a planar curve, so when you have a curve that's just in like the xy plane, for example, then the normal vector to that plane is parallel to b, the binormal vector. So if you've got a planar curve, then b is actually parallel to k. It's just like sticking up, right? Okay. So these 2 planes are integral to the concepts of curvature and torsion. We already talked about curvature. We're going to talk about torsion in just a minute here, but intuitively, curvature measures how linear a curve is, Remember, if the curvature was 0, then you had a line, right? That's what it is. Torsion measures how planar a curve is. How planar a curve is. So if your curve is not twisting up out of the osculating plane, like as you move around, if it's not twisting up, then it's not very twisty, right? So that means the torsion, the torsion yeah, there's not a lot of torsion. So that's what we're using these two for, curvature and torsion. Curvature is also intimately connected to circles, as we saw in example 3, when we saw the curvature is inversely proportional to the radius of a circle. And we're going to see that again in a moment when we start talking about osculating circles. Okay, so this is another one that I want you to try on your own. I want you to try to find the equations of the normal plane and the osculating plane of the circular helix at this point. So start by thinking about how you would start. All right, now say something out loud just to wake your brain up a little bit. Say something to your dog, your cat, your hand, your friend, whoever. And now try to compute it yourself. Equations of the normal plane and the osculating plane at this point. One good place to start is remember how we described a plane. What did you need to know to describe a plane uniquely? Or just describe a plane, I should say. All right, here we go. So if you remember, to describe a plane, we needed a point on the plane and we needed a vector normal to that plane. So this is where things can get fun because we have a point. Now we just need to find the correct vectors, the correct normal vectors. So the point P corresponds to t equals pi over 2. So the normal plane at this point will have the vector r prime of pi over 2. Or I should say a normal vector. It doesn't have to be even unital here. But this is a vector that is normal to the plane at that point. So an equation of the normal plane is this, or simply this. And that's what we get. So this is the equation of the normal plane. This is the equation of my hand right here. So that's the equation of my hand. And this pencil here is r prime. So what we did was we found r prime evaluated at pi over 2, and we used that to get the equation of my hand, which is this. Okay, now the osculating plane, that's the one that contains both t and n. So a normal vector to that plane is going to be b, the binormal vector. So b is orthogonal to the osculating plane. It's like sticking up out like this, right? So we have the point already. Now we just need a value for that vector at that point. So we plug pi over 2 into b of t, and we get this vector. This is like the direction of that vector, right? Well, with size incorporated as well. So then the equation of the osculating plane is this, which simplifies to this. All right. Okay, now we found equations for these planes. Now let's talk about osculating circles. So osculating circles are really important because they have a lot to do with, this is actually one of the ways they defined curvature way back in the day. But you might use them a lot if you're doing some engineering where you have gears and you have belts running over things. Osculating circles play a role in that type of engineering. So what is an osculating circle? The circle that lies in the osculating plane of a curve C at the point P, has the same tangent as C at P, lies on the concave side of C in the direction n points, and has radius rho, which is 1 over kappa. And that's what's called the osculating circle, or the circle of curvature. So this is why, this is basically originally how they defined curvature way back in the day. So what is the osculating circle more intuitively? It's basically the circle that best approximates the curve at a point and has the same curvature near there. So that's basically what it is. I'll show you a picture in a minute, but let's stick to the algebra first. Find and graph the osculating circle of the parabola y equals x squared at the origin. Let me see. This one I think I'm going to work out on my own, because then we got to get to torsion too. So basically what we're going to do is this. I'll start with a picture actually, and then I'll do the algebra. So here is the xy plane. Here is the parabola y equals x squared. The idea of an osculating circle is, what is the equation of the circle that best approximates the curve right here, right at the origin? That's what we're trying to find. So what are the conditions here? The curvature of the circle, it's going to match the curvature right here. The circle is going to lie in the direction of n, the normal vector, right? And its radius is going to be 1 over kappa, whatever the curvature of x squared is. Luckily, we have some of this information from earlier. In example 3, we found that the curvature at 0 was 2, using that formula and so on. So that means that the radius of that circle has to be the reciprocal of that, because the curvature of a circle is inversely proportional to its radius. So the curvature is 1/2, right? So the curvature is 1/2. Now, if the radius is 1/2, just lost my train of thought. If the radius is 1/2, and it is centered at 0, 1/2. Oh yeah, there we go. Just like a brain fart for a minute there. The radius is 1/2, and we know that this point has to lie on the circle. That means that this distance is 1/2. So now what we're looking for is we're looking for an equation of this circle right here. Well, we know where the center is, and we know what the radius is, so we can easily compute, or we can easily formulate the equation of the circle. And this is it right here. X squared, y minus 1/2 squared, r squared. So this is the osculating circle. Cool stuff. All right. Whew. Okay, trucking along, hang in there. Now we got to talk about torsion. So one of the things I mentioned before was curvature gives us information about how a curve bends at any given point. And dt ds gives us information about how the normal plane changes, because t is a normal vector to the curve, right? So the curve can also twist out of the osculating plane, and that was something I mentioned briefly earlier when we were looking at that animation. So if your curve is not planar, it can twist out of the curve. And that's essentially what we're trying to describe with torsion. We're trying to describe like how much the curve is twisting out of the osculating plane. Now, remember that B is a normal vector for the osculating plane, right? Here's B. So that means that dB ds is going to give us information about how the osculating plane changes, right? So what is the change of this vector with respect to arc length? Like so, just like that. Okay, so to do this, we're going to need a lemma, and this first lemma is actually one that is in that picture I'm going to show again. First, dB ds is parallel to n. It's parallel to the unit normal vector. What is the proof? The proof is on your homework, so you will prove this in the homework. We're not going to do it right now just to save time, because this has already taken a long time. But let me go back to that figure of the osculating and normal planes, and you can kind of see right here. So what we're saying here is that dB ds is parallel to n. And that's what you'll prove in your homework. You might even be able to think of how you could do it. How would you prove that two vectors are parallel? There's a couple of ways, right? Okay. So dB ds is parallel to n. We need that little lemma. Go back here. Proof is on the homework. And now we can proceed. So since dB ds is parallel to the normal vector, that means by definition, there is some scalar tau such that dB ds is equal to negative tau times n. Little note right here, it's actually just convention to include the negative sign here. So that way the value, you'll see, the value that we get for torsion agrees with the physical intuition given by the right-hand rule. That's the idea. So long story short, because these two things are parallel, we have this relationship here. The number t, or I'm sorry, the number tau here is what we call the torsion. So tau is called the torsion of C at a point P. Now, we're going to get some formulas for it here. Note also that n dot n is actually equal to 1. Why is that? Actually, ponder this for a minute. Why is n dot n equal to 1? Okay, I'll let you think about it. You can ask about it in class if you're curious. Now, if we dot both sides of this equation by n above, we get the following definition for torsion. This is the definition of torsion. So the torsion of a curve is basically dotting dB ds with n and taking its opposite. That's the torsion. All right, here we go. Familiar thing from the past, right? So we have this definition of torsion. As before, it's often much more convenient to be able to compute torsion when it's expressed in terms of the parameter t instead of the arc length s. So here we go. Chain rule once again gives that dB dt is equal to dB ds times ds dt. This lets us solve for dB ds by just dividing, and so we get dB ds is equal to this. But up here, dB dt is just b prime, and ds dt is r prime. Once again, length of r prime, sorry, length of r prime. And there we go. So now we have another formula for torsion. So how do you define the torsion of a curve? If you want to use the parameter, it's b prime dot n over the length of r prime. That's it. So let me flash back real quick. Let me do this. Here is the dot n part. So what we did was we rewrote dB ds as this, and then we dotted it with n, like that. That's what we're doing right there. Then we just use properties of the properties of the dot product to move the dot n up to the top. That's it. So here's a formula for torsion. Okay, now here's one I want you to try. So try to find the torsion of this helix that we explored in examples 1 and 6. You can use this formula. So think about how you're going to start. All right, say something out loud to yourself about how you'll start. A groan is okay. And then try to calculate it. What is the torsion of the helix? All right, here we go. Okay, so an example, yeah, we're going to put all these things together. This is why I keep reusing this example, because that way you don't have to recompute everything. But in example 1, we found that the length of r prime was root 2. In example 6, we actually computed the normal vector, a unit normal vector, and the binormal vector. So now we can compute the derivative of b prime, the derivative of b, which is that. And now, oops, sorry, wrong way. Now we can put it all together. So tau of t is the opposite of b prime dot n over length of r prime. And you can go through the calculation here and you get 1/2. There it is, 1/2. Okay, that is it. So hopefully you got the same example. So this is a good comparison. I like that the book has this. So let's compare the curvature and torsion of the following space curves. So look at this space curve here. This is just the unit circle in the xy plane. Its curvature is 1, again, because the radius is 1, and 1 over 1 is 1. But the torsion is 0. The curve is not twisting up out of the plane at all. So the torsion is 0. However, for this curve, things are a little bit different, right? Things are a little bit different. So the curvature is 1/2 and the torsion is 1/2. So the curvature is a little bit different because the osculating plane is changing. The osculating plane is changing. And the torsion is positive because you're actually leaving the osculating plane. The curve twists up out of that plane. So the torsion is not 0. That's the idea. Okay, next, there's one last formula. So again, this is another formula for computing torsion. What does it do? It frankly just gives you a systematic way of computing a few derivatives, and then you can do some cross products, some dot products, find some lengths, and it will give you another way of computing the torsion. So the torsion is also given by this formula right here. We are not going to prove it. You are welcome to try to prove it on your own. It's always a good exercise to prove these types of things on your own, but this is the formula. Remember, you do not need to memorize all of these formulas. It's much more important that you make sense of what curvature is and what torsion is. That's what's more important. You really should actually know how to compute the unit tangent vector, the normal vector, oh my gosh, the unit tangent vector, the unit normal vector, and the binormal vector, which is unit. Right, so that's what you want to take away from most of this, not all of these really complicated formulas. Okay, now let's finish up with this. So let's get a little bit of relief here. This is a section where Mathematica can really save you a lot of time, but I'll repeat this like I always say, just make sure to use the commands wisely. Don't rely on them entirely. Just make sure you're building your intuition and conceptual understanding for these operations. But again, there is a point where a human's job ends and a computer's job begins. And you need to get comfortable with that relationship. You got to ask yourself, could I do this by hand if I really, really had to? If I really had to, could I do it by hand? If you know that you could, you're in a good place. Then go to Mathematica, use some handy commands just to save you that time. And you can always test with Mathematica too. Like compute it by hand, plug them into Mathematica and see if you get the same answer. If you don't get the same answer, debug your brain or debug your code. That's the idea. So some handy Mathematica commands. One, we already have commands for the dot product, the cross product, and the derivative. So you can use Mathematica to your advantage in this case. The absolute value command is simply ABS. That is the absolute value command. So if you need that, you can. The command arc length will give us the length of a curve. The command arc curvature will give us the curvature of a curve. Aside from that, not every operation is built into Mathematica. You might be thinking that there's a lot of other things that you could compute. They're not all built in. There are but there are many custom commands developed by the Mathematica team that you can call from the Wolfram function repository. I have a few of them listed down here. The one thing is that these commands, you have to import them into your Mathematica notebook, but then you just use them like a regular command. And the import is simple. I'll show you in just a moment here. So some relevant commands to this particular section are tangent vector, normal vector, binormal vector, and curve torsion. So what I'm saying is Mathematica can do all of this stuff for you, but these particular commands are not like built in. So you have to have an internet connection, and Mathematica will call that command from the function repository, and then you can use the command just like you normally would. So let's switch to Mathematica and take a look. All right. Oh yeah, arc length. So here I have the arc length function. This is a built-in function, and I'm just finding the arc length of that circular helix, right? In fact, this is one of those times where I do want to flash back and forth. Where are you? Arc length, arc length. It's like 2,000 slides here. Where are you? Okay, so arc length of cosine t sine t t. If you remember from before, we computed that, oops, that the arc length, of course I picked the wrong one. Here it is, that the arc length was this. There we go. So the arc length of that helix from 0 to 2 pi was root 2 times 2 pi. Let's see what Mathematica gives. So I've got it entered here, shift return, 2 root 2 pi. So verified, it is the same. Nice. So keep this in mind to check your work. Arc curvature. So this was the curvature of the twisted cubic. Let's see, where was that one? That one had a pretty funky formula for it. Let me dig it up here. this it? Yeah, this is the one. So this is back on slide 27. I believe this is it, right? Let me double check. Yeah, here we go. The twisted cubic, twisted cubic t squared, t cubed. This is on slide 27. We computed the curvature function to be this. Let's see if Mathematica agrees. So arc curvature, I entered the vector function here. The parameter is t, shift return, boom. There it is, the same formula. Same formula. I'm going to flash back just so you can compare. It's right there in blue. There we go, right there in blue. Now let's take a look at Mathematica. Same formula, right? There it is. Cool stuff. Okay. Actually, you know what? Let me do this before I go to the next one. Remember, we also wanted to evaluate the curvature at 0. So, oh, see, do I remember this command? Let's do that. I think it's replace all. So I'm going to do this. I'm going to type replace all. And then I believe it's going to be t comma 0. I think this is how this command works. No, that's not right. Maybe t0. Oh, there it is. Yep. So t goes to 0. So replace all is basically replacing all of the instantiations of t after arc curvature is computed. So arc curvature gives us like the formula. Let me do this real quick. I'll show you again. Here we go. Arc curvature gives us the literal formula for any t. So now what I'm going to do is I'm going to say replace all and then feed that through. Oops, 0. And we get 2. And that indeed was the curvature that we computed. So flipping back, you can see we found that the curvature there was indeed 2. So it agrees. Good. That means we did it right. Okay, now let's go back. Here is how you call a function from the Mathematica function repository. And this one was curve torsion. I thought this would be a good one to finish up with. You type resource function, the name of it, and put it in quotes. And then you have this as the input. This is the input. So I wanted to find the torsion of the curve cosine t sine t t, which is that helix. And I believe that is the one we just did, right? Torsion, 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 come back, torsion. Torsion, I believe it is. Yes. Okay, let's see what we get. Okay, so this is one where it looks really messy, but it should simplify. Yeah, this is unsimplified. So this is one of those times where the calculations are a little bit too complex for Mathematica to instantaneously simplify. So what I'm actually going to do is I'm just going to tell Mathematica to simplify that. There we go, there we go. Okay, this is a little closer. Let me flip back to the slides for a moment. Notice here we computed that the torsion was actually constant. The torsion was 1/2. Let's see if we're getting the same result when we look back at Mathematica. Okay, right here, the numerator is 1. Here we have absolute value of cosine t squared plus absolute value of sine t squared. Well, cosine squared plus sine squared is 1. And 1 plus 1 is 2. So we get 1/2, which is 1/2. So this does agree again. There you go. Little smiley face just for fun. Okay, and I do believe that is it. So let me do this quick. Let me do this quick. Let's play. Thank you for hanging in there for this very, very long lecture. I apologize, but you can see this was just so packed full of information, so packed full of content. I hope you did take a break in the middle, but that's it for today, and I will see you all in activity. Have a good one, and thanks again for hanging in there and listening. Take care.